Good afternoon, everyone. Thank you for coming to the conference, and I'm Laya Chen, and I'm very honored to be invited by THPCA. And Bangkok is a great city, and I enjoy the stay here. All the speakers today have already talked a lot about reliability and all the tools and methodologies on testing PCB and some of the PCBA. The speech here I present today is going to be a little bit more specific on assessing via structures and PDH holes. I'm going to cover some of the more specific areas, such as assembly process survivability, reliability, and the robustness testing. When we talk about the reliability, it is all about the catch of all phrase of for good. We cannot talk about electronics without touching on the actual reliability. Even our company name is called Reliability Assessment Solutions. Everybody today wants to talk about reliability. But what is the actual reliability? When we talk about the PCB via structures and substrate, the reliability is more related on a few R. The word R can relate to solder process survivability, robustness, relative reliability, or the R square for PCQR square. Under reliability, there are different definitions on the concepts of these different things. When people want to emphasize the reliability, a lot of times we add high in front of reliability. And when we want to emphasize more, refer to super high reliability or ultimate reliability. I've already heard a lot of sayings. People add a lot of highs in front of the actual tests. For example, I've already heard a lot of HALT, HASS. They all start with highly accelerated. So people like to use the word high a lot. Just a little bit. Today, I'm going to talk a little bit, probably share some information on the tools for assessing the three reliability R's for via structures and PDH. The mostly commonly used tool, or very aged tool, or I would say has a very long history tool, is a very standard tool is what we call the microsection. Microsection is a tool to analyze and detect the physical properties and attributes of PCB and the substrates via structures and the PDH. There's another tool to evaluate or assess the electrical, and not another, some other tool to assess electrical properties of via structures PDH when we're testing for component attachment, solder survivability, and sorry, just However, when we test the component attachment process solvability, we need to include the worst case component attachment repair and rework process. Typically, for example, we have, in some cases, only 4 processes of assembly, maybe 3 wave soldering, 1 reflow. If you think this component attachment process simulation is done, it's actually not to choose. We need to add the worst case simulation into consideration. For example, when we test the solvability, survivability, we need to also count the repair and the rework. And sometimes, most of the time, the repair and the rework temperature is higher than the typical temperatures inside the reflow oven or wave soldering oven. So in the solvability, survivability test, we need to count not just the cycle quantities, but also the temperatures in the worst cases. All right. And there's another concept called robustness or relative reliability, what we call R-square simulation. This robustness testing or relative reliability R-square testing is actually considered the accelerated failure factors that can cause the product actually to fail a lot faster than the real life. And it would not count any of the actual, like for example, the work temperatures in the actual field. It adds a lot of the failure factors in the testing. Doesn't mean your products will experience these kind of temperatures in the end-use life at all. These, what we call robustness testing, will make the products to fail a lot faster than it should be, and we can use this accelerated test to actually evaluate, is this product better or is this product more reliable compared to the other one? This is what we call robustness testing. Robustness testing is typically used to compare or R&D purposes. And there's also the very literally reliability simulation. It doesn't add a lot of the failure accelerated factors in the actual testing. The reliability simulation is an acceleration of end product's operation environment without adding additional failure acceleration factors. Many cases, microsections are also combined with electrical testing, combined with this robustness testing and relative reliability testing or reliability testing itself. It is a very good evaluated tool after these tests. For many years, microsection is the only tool we can use to evaluate PCB via structures and the PATH. The benefits in manufacturing quality assessment is with microsection, we can tell a lot of things. For example, when we look at the microsection report, we can look at the layer thickness, the quality, and the construction makeup. For example, copper, resin, and the glass structures. And we can also tell the plating and the inner connection quality. Is there any cracks or separation, or how good the plating is? And the failure analysis to identifying problem. That's why I just said microsection is a very good tool combined in use with some long-term relative reliability testing or robustness testing or relative testing themselves. But it also has its own overreaching adaptations. For example, normally when we do microsection, we don't go to the field and just grab a board and do microsection, start right away. There are some preparation to be done before we start the microsection. Unless otherwise specified, that's by IPC standard, every microsection, every coupon or PCB board before microsection, you need to be treated by what do we call the thermal stress test. So the PCB themselves or the coupon themselves need to be treated first in accordance with thermal stress test to simulate what the PCB is going to experience in the assembly process. Typically, it is a solder part. Thermal stress is a solder part test. We take the PCB, we cut the PCB, and we put in the solder part several times, and float for a few seconds, take out, and float again. Sometimes like six times to simulate 6 times of the wave soldering and reflow, rework, and repair. So this is just all different times, different cycles of assembly soldering process. And it's also a assessment tool for reliability and robustness testing. However, microsection has its own benefits. However, it also has its own downsides. For example, microsection don't have enough data to make our own analysis. It just lacks of statistical significance. On one via structure, we have a 360-degree circumference. And when we do a microsection, we cut the via to the center via and grind and polish to only that maybe 2 points. We can only see 2 points of that whole 330-degree circumference. And all the structures behind the microscope are hidden or unseen. So what you see on a microscope is very limited data. And on one microsection, you can only test typically 3 vias. Sometimes for a very skilled person can be 7, 8 vias, but that's about it. And for small vias, it's even more difficult. A lot of times, a skilled person can only do 1 for some microvia structures. If you get more than one via, because the size of the via is just so small. You miss it one, for example, you missed one scratch, and that place is gone. The place you're supposed to evaluate is gone. So it's very difficult to get a very good view for very small structures. And there's limitations on microsection for accession via structures. It requires all the technician to start with a thermal stress test, which I just described a little bit, is to get a PCB or coupon cut to small area and do a flow sorter test. We developed this technology, we developed this test method, to actually simulate the assembly process. However, this test method is, of course, easy to operate. Just take the board, cut the board, and bake the board, and take the board to the solder pot. Dip a few seconds, take out. That's easy to do, easy to operate. But it also has its downside. It more closely simulates a through-hole wave soldering process instead of a surface mount Venction reflow. So if your board has lots of PDH holes, so this test is very good simulation, because it simulates like a PDH, the through-hole wave soldering process. However, if your boards get a lot of the surface mount components, so the typical thermal stress test does not simulate very well with your actual product. So that's a downside for typical preparation thermal stress test for microsection. And as we all know, the via structures and the PDH these days have continued to shrink in size and increase in complexity and the plane offset, which means it's almost impossible to microsection in bulk scale. You cannot microsection 1,000 or even like 500 in one day. In old times, when there are a lot of PDH holes, people do microsection like hundreds, sometimes thousands every day, because that's just easy to do. The holes are so big, easy to take the area, cut the area, and do microsection easily. However, when PCB and all the via structures are getting smaller and smaller, it's almost impossible to do a lot of microsections on these microvia structures in huge quantities. Just impossible. And it's very difficult to, by requirements doing microsection, we are required to get to the microsection evaluate point to stop at the center of the via. That's the center of the via, maybe by 5-10% offset is allowed, but that's about it. So we are supposed to stop at center of the via and start the evaluation. It's not that difficult to do on big vias, big PDH, but with a small vias, especially these days, everybody's going AI or the data center, everything is going smaller. So it's very difficult to stop at very center of the microvia. So making microsection very difficult to do. I know from the slides from the previous speakers, we've seen some good microsection photos, but that takes a very skilled person to accomplish. to do this kind of microsection, it requires some artistic or wizard level skilled technicians to get a good microsection on microvia. So all the slide, the photo on the slide we see from previous speaker, that's selected from hundreds of pictures. That's a very downside. And in today's everything's going high speed, the AI, everything's just going smaller. So we've already seen a demand for new methodology to evaluate the via structures PDH reliability based on performance, not just on appearances, on visual appearance in microsection. We cannot just look at the good-looking, pretty test report for microsection. A microsection report are like a dozen of pages. If you ever got a chance to look at the microsection report, there are at least 10 pages of report. Got lots of pictures with different measurements. But we need more than that these days to make sure it's a good and reliable product. And we've already seen a demand for new methodology, but some chance, some case actually happens, cause the industry to respond promptly for these demands. In some case, I would say some big headquarters, some big corporates in the industry who's done the AI and data center products have seen some of the products going past their previous products, past the electrical functional test, and some of the traditional burn-in test, they all passed. Even the thermocycling, everything passed. But they start to see issues. If the old concept was correct, they're not supposed to fail. However, the products start to fail randomly, sometimes not constantly, randomly. They start to fail randomly, then things getting worse and then fail forever. All the experts and failure analysis technicians and engineers, experts spend lots of time tracing back what caused this failure. And they find out that the failure was actually, the failure cannot be detected using standard tests. If you look at the graph on the right corner on the slide, you can see this is the failure they've seen is a separation between copper plating and target pad in microvia occurring during component attachment process. This is actually already happened during the assembly process, but none of those technicians or engineers thought about doing anything to monitor what's going on in the reflow process, in the assembly process. They just let the boards going through the reflow process, the reflow oven. Temperature is right, everything looks right, the oven temperature looks right, the board surface temperature looks right, the profile looks right, profile goes perfectly, everything goes past. Then they did the functional test at room temperature. It was all good. Then they started the traditional thermocycling test, and they all pass. But this kind of failure did happen. this kind of failure did happen. It was typically, it was caused by significant expansion of PCB materials. So after all the failure analysis research, all the experts start to realize that we need to do something to monitor what's going on in the real assembly process. So all the experts and the IPC committees come up to a test method called test method IPC TM650, test method 2.6.27. These test methods actually use coupons, which call IPC D coupons, to simulate the assembly process for many cycles, depending on your actual product assembly process. Sometimes can be 230 degrees C, sometimes for leaded PCB, but for 245 reflow profile, and also 260 for lead-free. For lead-free PCB, so we have different assembly process simulation temperatures. Then this test method also requires, during the reflow, we need to monitor the resistance change real time to catch any of the early failures which are already happening in the reflow process. Previously, we didn't pay any attention to the resistance change, to the electrical early failures. We didn't pay any attention. So these kind of failures, we just let it go, pass. But some failures can happen already in the later reflow cycles. For example, this is a test we've done. This is a test we've done to six cycles, and we monitor the resistance change. This graph on the slide is a resistance change graph. As we can see, the resistance on the peak, on the top of the cycle, already show resistance change getting worse and worse. In last cycle, it already passed more than 10 degree, more than 10% of the resistance change. It's an indication that this batch of coupons already shown a very early failure. And the slide on the bottom, the graph on the bottom of slide shows the coupons are already seeing open. It's not just a high percentage resistance change. It's already showing early open. These kind of failures are very sneaky, very tricky to catch, because these kind of failures can be self-healed. It can recover. These kind of failures will only occur at the peak of the reflow. As we can see, at the room temperature or at the lower temperature of the reflow, the resistance change seems to be normal. But the difference is at the peak of the reflow. As we can see, the resistance change start to fail, start to show very obvious evidence. However, this kind of failure can be self-healed. As temperature cools, all the copper structures will reconnect. And if you test at room temperature, all the resistance seems to be normal again. That's why if you don't do any of the resistance monitoring during reflow, you will miss this, because it recovers at room temperature. And sometimes it will not be detected at all. even after the thermocycling test afterwards. These kind of tricky or sneaky failures only happens a few seconds at the peak high temperature of the reflow. After these few seconds, it's gone. You will not be able to see it. And the finish, after these few seconds are gone, the finished product is electrically compromised, but it will pass all the electrical test. It will pass all the functional test and burning test. The component attachment process survivability testing. When we talk about what do we call survivability testing, is a test because every thermal excursion near or beyond the TG has a degrading effect on the organic material PCB and the substrate. It will fatigue and stresses the via structures and the PDH copper due to expansion of different materials, because the expansion factors are different of PCB materials and the via structures. And it also has a tempering effect on the via structure and PDH copper. It will change the grain of copper structures. When we want to start any of the process of component attachment, process survivability testing, we want to include the expected worst case repair and rework components, including cycles. We want to include all the repair, rework, reflow, all the cycles, and we want to include what is highest temperature. That's that's one way we will talk about the reliability is on component attachment survivability. Another thing we want to talk about is reliability testing of PCB and substrate. The reliability testing of PCB and substrate exposes organic material systems, via structures and PDH to temperature shock or cycling that exceeds the actual life expectations without adding additional failure acceleration factors. The upper temperature of reliability shock or cycling needs to be typically 10 degrees C or lower than TG of the PCB. That's when we don't want any additional failure factors. We just, at the high temperature, we just use anything 10 degree or lower than the material TG. For thermocycling, the low temperature is, in this case, on the graph, is -55. This temperature is also very commonly used these days, especially for some of the data treatment or AI GPU companies. And there's this example of thermocycling is done after the previous assembly process survivability testing. So after the assembly simulation, we will start typical reliability testing. During reliability, during the typical thermal shock or thermal cycling, this kind of reliability testing, we will let the coupons or PCB to expose in a hot and cold temperature cycling, and also monitor the coupon resistance change. With this coupon resistance change, we will be easily to determine if the structures are already showing some of the failures. There are some types of reliability testing technologies used. Today, we have a lot of customers that are already using a test system. It's called HASS2 test system. It also starts with HA. As I already said, there's a lot of tests start with HA. This test is called HASS. It's a shortened for highly accelerated thermal shock testing. It's a single chamber, and they use the compressed air as the thermal conductivity medium. And the coupons are fixed in the single chamber. Coupons are not moving at all. The chambers are not moving at all. It allows the airflow of the lowest testing condition to be -65. The high temperature can go as high as 265 degrees C. It can shorten the test cycles from typically traditional thermocycling test is 1 cycle per hour. With HASS2 testing, it can be shortened to 2 to 10 cycles per hour. And the HASS2 test system is also integrated resistance monitoring system. It can simulate the assembly process while monitoring the resistance change, but it can also simulate the thermocycling test while monitoring the resistance change. This is a typical example of a thermocycling test. And the test report. On the left part is 5 cycles of temperature cycling example. On the right part is the resistance change plot and the summary sheet to show coupons, which cycle coupon failed, and what is the maximum failure percent, and what is the center of the slide is a picture of a HASS2 system. The HASS2 system is a convection. It can test the convection reflow assembly simulation up to 265. It can also test the reliability and robustness shock cycling from -65 to 265. It can also test multiple types of coupons. We can typically test IPCD coupons, original HASS coupons, and single via coupons, solder joint coupons, and custom coupons up to 7 resistance nets per coupon. HASS technology was originally introduced in year 2000. No. The original HASS testers can only test from -55 to 160, and only specialized on HATS 2-net coupons. Right now, we have spent years of research, R&D on the research on developing HATS2 coupons. HATS2 testing services were provided by different kinds of third-party laboratories in the world in 2023. And the test system became available for purchase in 2025, last year. This is a video of the HATS2 test systems. It's easy to use multi-language software with multi-level user logging. It has a ruggedized control and monitoring system. All the measurement and switching systems to monitoring all the resin changes in a air-conditioned compartment. So all the temperatures are very stable to minimize any of the temperature drift caused resistant drift that can be false data. And we also has an automatic test chamber, opening and closing with safety interlocks. We use the machine itself use compressed air to heat and cool the coupons inside. It doesn't need additional like special air or special electrical or heating tool. It also has a very accurate flow control to get all the air past the coupon evenly. In one chamber, the system itself can test 72 IPCD coupons, as you can see on the left side of the slide, and 36 HATS or HATS2 coupons. Now we use custom press fit connectors with high temperature materials. Easy to adjust. And it's with plated gold, so all the resistance is very consistent. Nothing additional contributes to the resistance measurement. And it can just... I spent a lot of time talking about the reliabilities and different test methodology to test the reliabilities. The HATS2 test system also can test the convection reflow simulation and thermocycling test based on IPC standards. All the slides will be shareable to all the audience, so if anybody is interested later, you can use the slide to know more information or more knowledge about this. Sorry, just... Okay. And just let me get to the last slide, and I think... I have a lot to tell you about this, but our time here is very limited. So as the audience today will get a slide to share. You can know more information. But The HASS2 test I'm going to introduce you today is capable of doing the reflow, the assembly process control, and robustness testing, and reliability testing. The highly accelerated cycling test. It shortens the cycling from typically 1 hour to 6 to 10 cycles per hour. So typically for 1,000 cycles, you can, with traditional dual chamber thermoshock chamber, you need 42 days to accomplish thermoshock test. But with HASS2 coupons, with HASS test systems, we can accomplish 1,000 cycles in about a week. So all the research work is highly improved. All right. I think my time here is up, and I'm going to get the last slide. Still quite big to go to the last slide. All right, I'll share the slide with the group, and if anybody needs a slide, you can contact the organizers.